of functions given by f sub n of x equal to x to the n, that's a nice continuous function. Its graph looks like that depending on what n is. We found that these converge pointwise to this piecewise function whose graph looks like that. Is that a continuous function? Yeah. So you can find a sequence of continuous functions that converge pointwise to a non-continuous function. So that means you can't use a sequence of continuous functions converging piecewise to deduce a continuous limit. So no is a plurality and no is correct. On the other hand, let's ask another interesting question. Suppose f sub n is continuous for every natural number n, and the sequence f sub n converges uniformly to this limiting function f. Then does it follow that the limiting function f is continuous? How many people would want to say yes? I mean, but kind of that's guiding, right? Or maybe you've looked at the next bit of notes because I gave those to you, which you prove that that says. Well, I guess that makes it silly. How many people would want to say no? Okay, so no one's just so on. We'll prove that in a moment. Here's another question. Suppose you have a sequence of functions f sub n converging to this limiting function f. Let's suppose that the limit as x goes to c of f sub n of x is L sub n. So, right, there should be an n on the right-hand side. That is something that's different for different choices of n. Let's suppose that the limit as n goes to infinity of that sequence of numbers, L sub n converges to L. Does it follow then that the limit as x goes to c of the limiting function f is equal to L? Said a different way, can I switch the order of limits? Should the limit as n goes to infinity of the limit as x goes to c should be the same as the limit as x goes to c of the limit as n goes to infinity? Let's see, how many people would want this, the answer to be yes? Not how many people believe it's yes, how many people would want that answer to be yes? Yeah, that seems like something we would like. So I guess like now I'm asking different questions for the yes no thing. How many people think that the answer is no? And we have a counterexample. Let's check out this sequence of functions. So let's take the limit as n goes to infinity of the limit as x goes to 1 of x to the n. Let's just determine what that is. What's the limit as x goes to 1 of x to the power n, where n is fixed? 1. So this is the same as the limit as n goes to infinity of 1. What's the limit as n goes to infinity of 1? 1. Now let's switch the order and see if it changes. Let's compute the limit as x goes to 1 of the limit as n goes to infinity of x to the n. And here I guess I'm going to specify that I only want to consider x values that are a little bit less than 1. Gesundheit. So if I take an x value that's slightly less than 1, an x value in the interval from 0 to 1, and I plug it into x to the n, and then I take the limit as n goes to infinity. What's the limit as n goes to infinity of x to the n then?
0.
0. So this limit will become the limit as x goes to 1 of 0, which is 0, and you'll notice those two aren't the same. So when you have a sequence of functions that converges pointwise, you might not be able to switch the order of limits, which seems really upsetting, right? There shouldn't be any non-commutativity there. There is. Question 2b. Suppose that I change the problem to require a uniform convergence. So suppose that f is the uniform limit of a sequence of functions f sub n. And then I play exactly the same game. I take the limit as n goes to infinity of the limit as x goes to c of f sub n of x. Compare that limit as x goes to c of the limit as n goes to infinity of f sub n of x. Well, I mean, I guess I'm doing too much guiding. What do you think? Should they agree to add the word uniform? If the word uniform is good for anything, they better. If they don't, then we need a concept other than uniform convergence to pull this off. And let's see, maybe before we prove those two theorems, which is the main goal today, let's just go through another example of verifying a sequence of functions converges uniformly. So here's a sequence of functions. Let's let g sub n be the sum from k equals 0 up to n of x to the power k. I claim that that converges uniformly to the function 1 over 1 minus x, at least on the interval negative a half to positive a half. Let's try to prove that. And the proof, in fact, will be pretty straightforward. So we'll take advantage of the fact that g sub n really has a closed formula, right? The sum from k equals 0 up to n of x to the k is the same as 1 minus x to the power pi over by 1 divided by 1 minus x. Well, let's do it. Let's consider any epsilon bigger than 0. We'll let n be something that we get to pick. We'll consider any little n bigger than big N and any x in the interval. Right, that's the order, that's where the x needs to go if we want to prove uniform convergence. We can't declare x before n. Then we need to show that the alleged limit minus g sub n of x is less than epsilon. So let's expand that out and see what that becomes. That'll become 1 over 1 minus x minus 1 minus x to the power n plus 1 divided by 1 minus x. And that's just like substituting it. What does that simplify down to? Yeah. And maybe I'll even put absolute value bars in there in some interesting way. Cool. Well, next, I think a pretty good place now. Maybe I'll interchange these. No, I'll follow the clause. So this x is in the interval from negative a half to positive a half. So what's the biggest x to the power n plus 1 could be? 1 half to the power n plus 1 even. So this is less than or equal to 1 half raised to the power n plus 1 divided by, let's see, x is a number that's between negative a half and positive a half. So maybe a picture is in order. And the absolute value is like the distance from x to the number 1. If x is a number that's between negative a half and positive a half, what's the closest x can be to 1? 1 half. So the absolute value of x minus 1, or 1 minus x, is bigger than or equal to 1 half. And I guess, like, that should obviously simplify, right? 1 half to the n plus 1 divided by 1 half is the same as. want to get down to the point where like there's only an n there, so I can like set that equal to epsilon and solve for big N. That's the way this game usually plays. So I'd like to get a big N there. If I replace that 1/2 to the little n by 1/2 to the big N, well, little n is bigger than big N, so which is bigger, 1/2 to the little n or 1/2 to the big N? To the big N. Do you think you could set that equal to epsilon and solve for big N? Yeah, I guess you would say, well, that's 1/2 to the big N equals epsilon. 2 to the n is 1/epsilon. Big N is the log of 1/epsilon. Cool, which is in fact, oops, that's a problem. Less than or equal to epsilon is what matters. So let's just go ahead and check that this is actually correct. The choice of big N we came up with, it depends on epsilon, that's great. Does it also depend on x at all? No, that's important. Otherwise it wouldn't be a proof of uniform convergence. And maybe we'll just go through a quick check. So we considered any epsilon, we came up with a big N. So that means for every epsilon there exists a big N. We then considered any little n bigger than big N and any x in the domain. That means that for every little n bigger than big N and every x in the domain, we proved that absolute value of 1/1 minus x divided by g sub n of x is less than epsilon. So we get that's less than epsilon. There's the definition of uniform convergence. This is actually a proof of uniform convergence. People feel pretty good about that? Yeah.
So can n always be based off of like the bounds of x, even though it can't be based on x?
Yeah.
Okay.
Yeah, so the 1/2, if you like, is chosen before the problem begins.
Okay.
So that 1/2 is a constant. That big N can depend on that 1/2. So if you like, maybe you would say, well, Chris, why were you, like, you could have proven something better. You could have proven for every constant c, which is strictly between 0 and 1, the sequence of functions converges uniformly from negative c to positive c. We could have proven that.
Mm-hmm.
And the only reason I didn't is because I wanted something slightly more explicit. But yeah, then the different choices of big N would depend on what C you used.
Mm-hmm.
But that's fine. You would choose the big C before you checked for convergence. Nice. So let's prove those things that I asserted are true. And let's start with the continuity plane. And let's draw a picture, if you like, of the proof before we prove it. So, well, let's state the theorem. Let's suppose that f sub n from u to r is a sequence of continuous functions. Let f be the uniform limit of the sequence of functions f sub n. Then the limiting function f is continuous on the domain. That's what we want to prove. So that should be like, okay, so if I consider any positive number epsilon, I can take x close enough to some point p so that absolute value of f of x minus f of p is less than epsilon. That's what continuity means. And let's see if we can pull that off. So here, if you like, is, let's zoom in a little bit. There's the graph of f sub n of x. And here is just a little epsilon neighborhood of that function. So I've drawn this tube going up and down by epsilon from the graph of the function. So by the definition of uniform convergence, you couldn't see that, it was off the screen. By the definition of uniform convergence, you know that that f of x has to lie in this little tubular region for every choice of x. Because you know that the absolute value of f of x minus f sub n of x is less than epsilon as long as you pick little n to be big enough. So that means whatever the value of f of p is has to be somewhere in this region. Whatever the value of f of x is has to be somewhere in that region. And let's just see how much control we might have. Now this function f sub n is also continuous, right? So that means as long as this p and that x are close enough, that means that this y value and that y value, we can get that distance to be less than epsilon. Everyone following me so far? It's very slow. I mean, I guess in some sense that's the point. So let's just see how close we can get these values to be to each other. So by continuity, we can get absolute value of f sub n of x minus f sub n of p to be less than epsilon. But since f of p and f sub n of p are also within an epsilon of each other, I guess that's just a yes. We can get f sub n of p minus f of p to be less than epsilon, and simultaneously get f sub n of x minus f of x to be less than epsilon. So by does that mean that we have do we have enough information to play a triangle inequality game? Yeah. So what will we wind up doing? We'll say, well, f of x minus f of p, that should be less than or equal, well, equal on the nose first, to f of x. I know that f of x is close to f sub n of x. So that's a reasonable move to make. But I know that f sub n of x is close to f sub n of p by the continuity of f sub n. So that's a reasonable move to make. But I also know that f sub n of p is close to f of p. So I mean, that's an equality no matter what I know. How close right now do I have the difference between f of x and f sub n of x? Less than epsilon. And this difference is less than epsilon by the continuity stuff. And that last difference is also less than epsilon. So just by drawing this picture, how big is the difference between f of x and f of p? Like 3 epsilon. So, but we know how to fix that, right? We're going to wind up dividing an epsilon by 3, it looks like. So, how many people feel pretty convinced of this theorem now? And let's even try to come up with the proof. So, let's prove the theorem. Let's suppose that f sub n from U to R is a sequence of continuous functions. So that means for each n, f sub n is a continuous function. Let's let f be the uniform limit of f sub n. Let's consider any p in U. I need to show that f is continuous at p. Because that's all that continuity means. Being continuous on a big set means that you're continuous at every point in the domain. So let's do it. So the first thing that we'll do is we'll come up with this neighborhood. So there exists some big N, so that for every little n bigger than big N and every point in the domain, I've called it U because I'm going to want to plug in different things. So I don't want to pick a name that's going to get used again. It follows that for every U in U, I can get the absolute value of f sub n of U minus f of U to be uniformly small. So I can get that less than any positive constant. What positive constant should I use? 1/3 of epsilon. I would have said epsilon over 3, but I guess, oh dear, how do you draw a 3? That. Cool. So, now we have a choice, this choice of big N. Now notice we don't include continuity. So in the definition of continuity, there is no big N. So I mean, that's weird. Our final answer can't have a big N in it. But let's use that big N. Let's consider any little n bigger than big N. So let's pick some little n bigger than big N because we know that for every little n bigger than big N, we have this inequality. Now let's use continuity of f sub n. Since f sub n is continuous at p, there exists a delta, which happens to be bigger than 0, such that for every x in the domain, if x is within a delta of p, then the difference between f sub n of x minus f sub n of p can be as small as we could possibly want it. So I think one thought of epsilon again. And now, just like we saw in like the pre-argument, we can play a triangle inequality game. The absolute value of the difference between f of x and f of p is the same as the difference between f of x and f sub n of x plus f sub n of x minus f of x add and subtract f sub n, add and subtract f sub n of p, which, I mean, you know what I'm going to write next. Like, I'm going to use the triangle inequality to break that into 3 pieces with absolute value bars around each piece. That's less than or equal to the absolute value of f of x minus f sub n of x plus the absolute value of f sub n of x minus f sub n of p plus the absolute value of f sub n of p minus f of p. And, well, we know that f of x minus f sub n of x is less than one thought epsilon, because this is true for absolutely every u in u. X is a thing in u, so this is true where we replace u with x. That's less than one thought epsilon plus. What's the difference between f sub n of x minus f sub n of p? What is that less than? One thought epsilon, because the absolute value of x minus p is less than delta. Plus the difference between f sub n of p minus f of p. What's that less than? One thought epsilon, where that's this line again. Okay, that's equal to epsilon. So that completes the proof. So notice, we really do need uniform convergence to run this argument. It was really important here that this choice of big N was the same no matter what input we used. Otherwise, we would have said, okay, so let's take x and p really close to each other. But then I don't know how big this little n needs to be to make that small, how big that little n has to be to make that small. And once I make those too small, maybe I need a different choice of delta to make this small. So you can't have everything depending on everything else like that. One of them needs to be uniform. How does everyone feel? That proof seem okay? What do you think? If I add the word uniform in the statement of the theorem, if I make this sequence of functions a sequence of uniformly continuous functions, do you think I'll get uniform continuity of the uniform limit? Do you think you see how the proof should go? Well, then I'll encourage everyone on problem 2 to talk to Maggie.
No.
I mean, I do encourage you guys to talk to each other on the homework. Well, maybe I'll do one last thing. Let's point out that this isn't a proof of uniform convergence. In particular, here's this choice of delta. Oh, that delta better be bigger than 0. As written, does this delta depend on the choice of p? Yeah, well, in particular, I chose the delta after p, so it automatically can. And in fact, it does, because f sub n is just continuous. Different p's might get different deltas for that f sub n. So there's something that would need to be changed, but I don't think it's anything too drastic. There's one other result that I promised you. Suppose you have a sequence of continuous functions. Suppose you look at a limit point of the domain U, so you can talk about the limit as x approaches c. Suppose that for every little n and big N, the limit as x approaches c of f sub n of x is equal to L sub n. In particular, assume that that limit even exists. If f is the uniform limit of f sub n, then the limit as x approaches c of f of x and the limit as n goes to infinity of L sub n each exist. Moreover, they're the same. So I won't even need to assume either of those two limits exist. I'll prove their existence as a consequence. So let's try to come up with that. So let's set this up. Let's let f sub n from u to r be a sequence of continuous functions. Let's suppose c is a limit point of the domain u. And suppose that for every n and n, the limit as n goes to c of f sub n of x is equal to L sub n. In particular, assume that limit exists. Let's let f be the uniform limit of f sub n. I need to show that these two limits each exist and that they agree. Well, one of those is like the limit of a sequence of numbers. What's the best way to show that the limit of a sequence of numbers exists? Show that it's Cauchy? That'll do. Let's try to do that. And well, let's just go through the proof. I don't have terribly much time. So let's see. If I want to prove this is a Cauchy sequence, I better consider any epsilon bigger than 0 and then come up with a choice of big N. And the only sequence information I have right now is that f sub n converges. So that's how I'll get my big N. So consider any epsilon bigger than 0. Since this function f is the uniform limit of the sequence of functions f sub n, it follows then that there exists a big N, such that for every little n bigger than big N and every point in the domain, the absolute value of f sub n of u minus f of u is less than, well, epsilon, though maybe we all know that I might wind up having to divide that by 3 or 4 or 5. So that means, so right now I'm going to kind of imitate the proof that convergence implies Cauchy. So that means that if I consider any little m and little n bigger than big N, then the difference between f sub n of u and f sub n of u is less than, well, is equal to, add and subtract the absolute value of f of u. That's less than or equal to f sub n of u minus f of u plus absolute f of u minus f sub m of u. What bounds do I have on that? Absolute value of f sub n of u minus f of u is less than, this amount is less than epsilon. So right now that's a 2 epsilon, so maybe that's an argument to divide the epsilon by 2. But I mean, that's not terribly good yet. So I fix now those two choices of m and n bigger than big N. I know that the limit as x goes to c of f sub n of x is L sub n. I know the limit as x goes to c of f sub m of x is L sub m. So let's see what that means. That means that I should be able to get L sub n really close to f sub n of x by having x close enough to c. I should be able to get L sub m really close to f sub m of x by having x be close to c. But f sub n of x and f sub m of x are pretty close to each other. So that means L sub n and L sub m are pretty close to each other. That's all the Cauchy means. So I think I see how to finish this proof. So there exists some positive numbers, delta n and delta m, bigger than big N, bigger than big N, such that if 0 is less than x minus c is less than delta n, then the difference between f sub n of x and L sub n is less than, well, I'll continue putting epsilons here. If 0 is less than absolute value of x minus c is less than delta m, then this is also less than epsilon. If I give you two different positive numbers, so it looks like I need an x value that's simultaneously less than both of these positive numbers. How can I guarantee that?
I have a question.
Yeah.
Why did you assume that delta sub n is greater than big N and delta sub m is greater
supposed to be bigger than zeros.
Okay.
So because of blood pressure concerns, I've been trying to really cut down on my coffee intake the past week, and today I'm really starting to feel it. I don't think I'll fall asleep in class. Maybe if it were a 2-hour class, I might. Yeah, those deltas should be positive is all I was trying to do. If you have two different deltas, you need to be smaller than both of them. You should be smaller than the min. So let's let delta be the min of these two things, and assume we have an x value that's within that delta of c, which we can, right? C is a limit point. Otherwise, we can't even talk about these limits. So let's do that. So L sub m minus L sub n, we kind of know exactly what we need, right? And I think I'll even combine these two steps into one. The difference between L sub n and L sub m by the triangle inequality is less than or equal to the absolute value of the distance from L sub n to f sub m n of x plus the distance from f sub n of x to f sub m of x plus the distance from f sub m of x to L sub m. So this is true by adding and subtracting f sub n of x and f sub m of x and applying the triangle equality. Everyone feel pretty good right now? And let's see. By the numbered inequality 4.1, which one of these ingredients can I conclude is small?
X minus f times x.
Yeah, because this is true for everything in the domain, and x is a thing in the domain. So, plus 2 epsilon by 4.6 isn't even valid. 4.1, 4.2, and 4.3. By 4.2, which one can I conclude is small?
F of n sub x.
Yeah.
Minus L sub n.
That one. And then by 4.3, I can conclude that the other one is less than epsilon. So I wind up with the 4 epsilon here. So this isn't a proof of any sort of Cauchiness yet. What do I need to do? Divide my epsilon by 4. And I think that I won't even bother doing it. You can do it. Nice. Okay, so that means the sequence of numbers L sub n is a Cauchy sequence of numbers. What do I know about Cauchy sequences of numbers? They converge. So let's let L be the limit of L sub n. It still needs to be shown that the limit as x approaches c of f of x is equal to L. And I think that I'm not going to have time to write down the detailed proof. Instead, I think that I will do this. Let's draw a picture of the proof. So I want to conclude that this limit L is the limit of f of x's so that's what I want. I want that length to be less than delta when the absolute value of x minus c is less than, when 0 is less than the absolute value of x minus c is less than delta. I want that to be less than epsilon. What's something that I know is close to L? Well, what's L by definition? The limit of L sub n. So that means I should be able to get L really close to L sub n I can get that to be less than epsilon when little n is bigger than big N for some number of big N. What about this x? What can I get that f of x to be close to? F of n of x. And that's independent of what x value I choose. So I've got two different choices of big N right now, one coming from the convergence of the sequence of functions, one coming from the convergence of the sequence of numbers. Can I get f sub n of x to be really close to L sub n? What's L sub n by definition?
The limit of f sub n of x as x approaches c.
Of that, yeah. So can I get those two things to be close by making 0 less than the absolute value of x minus c is less than delta for a small enough delta? Yeah. So I can get this length to be less than epsilon by taking cool. So that means that, well, I guess this tells us two things. That tells us that we should, I believe the result, so we can come up with a proof. The way that we drew this rectangle, I guess, tells us the order the proof is going to go in. First, we'll come up with some different big N's for L sub n and f sub n. Once we pick those two big N's, I'll consider a little n that's bigger than the max between those two big N's. Then I'll use the fact that f sub n of x converges to L sub n to say, that's how close I need x to be to c to get this whole thing to be less than delta. I guess it also tells you these epsilons need to be divided by 3. So it took us 3 steps. Cool. So I'm a few minutes over now. Here's what I'll suggest you guys do. There's a weekend before we meet again. So try to fill in the blanks in the rest of this proof, and also correct the typos. I think there are lots of other deltas that need to be assumed to be bigger than 0. Do that, go through the homework, and I'll answer any questions you have about anything on Monday.